We learned in class last time that Ernest Rutherford in 1909 proposed a new model of the atom. This new model was based on the results of a now famous alpha particle scattering experiment. Rutherford envisioned that the atom was a mini solar system in which each electron traveled around the nucleus like a planet travels around the sun. Well, this model is still used to explain the atom to elementary school age children, but our modern adult version of the atom is no longer a solar system model. What is the modern model of the atom, and how did we arrive at it? Well, one of the most important pieces of evidence bearing on our modern understanding of the atom is this. It's the light emission spectra displayed by elements. Allow me to explain. When light from the sun passes through a slit and is then spread out by a prism, you see a rainbow of colored bands. It's a continuous band of colors. Adjacent colors blend into each other. There are no breaks or dark bands in the spectrum. This is called a continuous spectrum. On the other hand, suppose we take an element and energize it, either through heating to a high temperature or by passing a high voltage electrical current through it. This will cause the element to emit light. If we take this light and pass it through a slit, then spread it out with a prism, we see something very interesting. We no longer see a continuous band of colors, rather we see a set of narrow lines of light separated by dark bands. We refer to this spectrum as a line spectrum. Every element, when so energized, produces a characteristic line spectrum. One of the simplest element line spectra that we can observe is the line spectrum for hydrogen. Its line spectrum consists of 4 lines of light, 2 violet lines, a green line, and a red line. These 4 colored lines of light are, of course, in the visible region of the light spectrum. If we examine the invisible portions of the light spectrum for hydrogen, we also see narrow lines of light, both in the infrared and ultraviolet region. Not shown here, in this region here is the ultraviolet. We can see also narrow lines of ultraviolet light. This region here, it's not shown, but we can see invisible infrared lines. With spectrometers, we can measure the wavelength of each of these lines of light, and we can measure it very accurately and precisely, actually to several significant figures. We also note that each wavelength of light in the line spectrum will have a corresponding frequency as well as energy. Here is the more complete line emission spectrum of hydrogen. Visible region, lines in the ultraviolet, and lines in the infrared. All right. Johannes Rydberg, a Swedish physicist in the late 1800s, discovered that the frequencies of the light produced in the line emission spectrum of hydrogen follow a mathematical formula. Here is the formula here. Now, this is simply empirically derived. It's not based on any theoretical model. He just noted, by examining it carefully, that it fit a pattern, a mathematical pattern. This formula, this equation, allows us to calculate the frequency of each of the lines of the emission spectrum of hydrogen. This is the wave number, nu with tilde. It's measure of frequency. It's equal to 1 over the wavelength. This equals a constant, capital R, that's called the Rydberg constant today, times a quantity that contains 1 over a parameter called m squared minus 1 over another parameter n squared. Now, the m values are integer values. They could be 1, 2, 3, and 4. N values are 1, 2, or 3 units higher than a given m value. So by plugging in various possible values of m and n, carrying out the math, you will arrive at a frequency that will match one of the frequencies of the observed lines of light and the emission spectrum of hydrogen. That's a pretty significant find. By the way, the Rydberg constant for hydrogen in wave number units is the value shown here, 1.097 times 10 to the 5th reciprocal centimeters. Let's now explain what happens when an energized atom emits light. Right. When an atom absorbs energy, either from an electrical source or by heating to a high temperature, we say that it becomes energetically excited. Now, it will not remain in the energetically excited state for very long. After a short lapse of time, it will release all or a portion of its energy, and will do this in the form of a light photon. Now, it's important to understand what happens when an atom absorbs energy. When energy is added to an atom, it's the electron of the atom that gains the energy, not the nucleus. When the electron gains energy, it moves further away from the nucleus, increasing its potential energy, and as well moves faster. That is, its kinetic energy increases. Now the important thing is this. The fact that we observe only specific wavelengths of light in the line spectrum of an element, or put differently, the fact that only certain specific energies of light are seen in the emission spectrum, tells us something important. It tells us that the electron in an atom can possess only certain specific quantities of energy. This is a very significant find. Now, in terms of our everyday experience with particles, this behavior is not typical. It's unusual. For example, if you throw a baseball, there's no restrictions on the kinetic energy that you can impart to the baseball, or for that matter, the potential energy. But an electron in an atom behaves differently. It operates by a different set of rules. In fact, these are called quantum rules. Now, the energy that an electron in an atom is allowed to have can be shown by the graph here. This is for the hydrogen atom. In this graph, each horizontal line corresponds to an energy the electron can possess. Each of these lines is called an energy level. The lowest possible level we denote as n equals 1 level. The next highest possible level is n equals 2. The next highest, n equals 3, n equals 4, n equals 5, and so forth. Let's use this diagram to explain how energy is released by an energized hydrogen atom. Now, before energy is absorbed by the hydrogen atom, the electron in the atom lies in the lowest possible energy. That's the n equals 1 level, sometimes called the ground state level. Now, we pump energy into the atom. What happens is the electron will move to one of the higher energy levels. The level that the electron is promoted to depends on the amount of energy absorbed, and it's a random process. We add energy to the atom. Electron starts at n equals 1. It could move to n equals 2. It could move to n equals 3. It could move to n equals 4, n equals 5. It's random. Now, let's suppose that energy is absorbed, promoting the electron from the n equals 1 level to the n equals 3 level. The hydrogen atom is now, we would say, energetically excited. After a short time, the electron in the n equals 3 level will fall to a lower level. Now, it could fall either to the n equals 2 or the n equals 1. It's a random process. When the electron drops from a higher to a lower level, it obviously loses energy. The energy that it loses will be released by the atom in the form of light energy, namely a light photon. In our case here, in our diagram, where the electron promoted level 3, we'll be showing it dropping to n equals 2 level. It turns out, well, when this happens, it's going to release the energy in the form of a photon, and it turns out that this photon of light corresponds to the red line observed in the line spectrum for hydrogen. All right. Now, along comes Niels Bohr, 1919, Danish physicist. He proposes a new model of the hydrogen atom. This model is a mini solar system model, and it takes into account the fact that the electron in an atom is restricted to being at specific energy levels within the atom. Now, of course, a hydrogen atom consists of one proton at the nucleus, and it has one electron outside the nucleus. We'll start with a normal hydrogen atom that's not energetically excited. In the Bohr model, the electron occupies a perfectly round orbit around the nucleus. Let's see, I think I have a picture here of that, right here. This is a picture of the Bohr model. In the unexcited state, the electron lies on the lowest possible orbit. It's called the n equals 1 orbit. Now, there are additional higher orbits. The next higher one is called n equals 2 orbit, and the next higher one n equals 3, then n equals 4, and n equals 5 orbit. Now, interestingly, in Bohr's model, he was able to actually calculate the size of each of these orbits, namely the value of the radius of each of these orbits. Now, importantly, he was able to compute the energy that the electron has occupying each of the possible orbits, n equals 1 orbit, n equals 2 orbit, and so forth. Right. How did he do that? What's the mathematical underpinning of his model? Well, Bohr made a number of key assumptions, arriving at his picture of the hydrogen atom. First, he assumed that the angular momentum of the electron is restricted to discrete quantities. Now, angular momentum, if you remember from physics, is given by the quantity mvr. M is the mass, v is the velocity, r is the radius. The assumption here is that in the hydrogen atom, the angular momentum of the electron is restricted to discrete quantities, and that's given by this expression here. N times h is Planck's constant divided by 2 pi. N can have an integer value 1, 2, or 3. The n that we're seeing here, in fact, corresponds to one of the orbit numbers, and you could say also it corresponds to one of the possible energy levels that the electron can be at. So that's one important assumption, that angular momentum of the electron can't be just any old value, it's restricted to discrete quantities given by this expression. Secondly, he assumed that the electrostatic attraction between the electron and the proton, the attractive force, is numerically equal to the centripetal force that acts on the orbiting electron. And that's a very reasonable assumption. So combining these two assumptions, Bohr was able to derive an equation that calculates the energy of the electron in a given orbit given by the n value. And here's the equation. It looks a little complex. E sub n, where n corresponds to the orbit number, or you could say energy level number. It equals a negative value of this quantity, with all those parameter values here, divided by n squared. N is the orbit number, or the energy level number. It's n squared. The negative sign is interesting in that the calculated energy will always be a negative value. The energy can be in joules, and it will actually have a negative value. There's an interesting reason for that, because the assumption is that if the electron is completely removed from the nucleus, here the proton, those two separated particles infinitely separated, will have zero energy. As the electron approaches, if you bring that electron back in to the vicinity of the nucleus, gets closer and closer, and now enters that, of course the energy of the electron, its potential energy, must go down. If it starts out zero, infinitely separated, and gets close enough to the nucleus to enter the area of the nucleus, its energy must go down. If it starts out zero and then decreases, it must have a negative value. That's why the negative sign is there. Now, each of these quantities, well, let's explain. 2 and pi are obvious. M is the mass of the electron, and the value of that is known. It is also known back in Bohr's day. The small case e to the fourth, that's the E is the electrical charge of the electron. For example, it can be expressed in coulombs. This is divided by h squared. That's the famous Planck constant squared. And the whole quantity is divided by, of course, the n squared. Now, the values for all these parameters are known. The mass of the electron is known, the charge is known, the Planck's constant is known. If you plug in values for all those, and that would give you the value for this expression here. Plug in the known values, you come up with 2.18 times 10 to the minus 18 joules per atom. So we can greatly simplify this equation by substituting the known values, boiling it down. We get this simplified version of the famous Bohr equation. The energy of an electron in an orbit equals minus the Rydberg constant. That's the value of the quantity here, the expression here. That's called r sub h, divided by n squared. N is the orbit number. The lowest orbit is n equals 1, the next orbit n equals 2, and so forth. Now, the significant thing about this is that this model is very successful. By using his energy equation, Bohr was able to correctly calculate the wavelengths of all of the lines in the observed emission spectrum of hydrogen, both in the ultraviolet, infrared, and visible regions. Well, that's a pretty good accomplishment. Now, I mentioned that Bohr has an equation that calculates the radius. I don't have that expression. In fact, I'm thinking about making that a project for you to work on. See if you can derive the expression for the radius, and then use it. We'll talk about that in the future later. We can't verify Bohr's computed orbit radii values because by modern standards we don't believe the electron travels on round orbits. So how does the modern model describe the motion of the electron in an atom? What is the right description according to the modern model? As we'll see, this modern model abandons the idea that the electron travels on specific paths or trajectories. The electron is doing something very different. Well, what, pray tell? Well, let's discuss this. I'll also mention that the Bohr model, very successful for the hydrogen atom, experienced huge problems trying to describe the line spectra of larger elements, like helium or lithium. It just broke down. As well, the Bohr model really offers no good explanation as to why the electron in an atom is restricted to specific energy levels. So a number of issues there to explain. All right, so moving ahead in history, we now come to a famous French nobleman, Louis de Broglie. As a graduate student in physics, working on his PhD dissertation, it was theoretical in nature. He did some important thinking. It was known at the time that light exhibits particle-like behavior. A light photon is a light wave, but it also acts like a particle. Light photons can ricochet off particles, just like a particle would ricochet off another particle, for example. If he further reasoned that if light photon can behave as a particle, the electron, known to be a particle, could correspondingly behave as a wave. That is, could exhibit wave-like properties. Well, that's a revolutionary thought. The idea is this, that when an electron moves, it is accompanied by a wave. The way that I always view it is that an electron in motion is accompanied by an oscillating force field. That's a kind of wave motion. Now, we're not saying what the size shape of the electron is. We're not saying that it's a bead-like thing. We're just saying when it moves, it's accompanied by a wave type of motion. He, through thinking, came up with an equation that calculates the wavelength of this electron wave, particle wave. And it's a simple equation. The wavelength of the electron wave equals Planck's constant, where we've seen that before, divided by the mass times the velocity of the electron. That would be the linear momentum of the electron. Well, fine and good. It's a theoretical equation. It might have just passing academic interest if it weren't for the fact that actually some other researchers were able to experimentally verify that equation. Davidson and Germer, and also Thomson, the son of J.J. Thomson, who discovered the electron. Let me tell you about their experiments. They did experiments that really confirmed de Broglie's theory, and, well, basically this. When you take a beam of X-rays and pass it through a crystal, the X-rays are spread out into a characteristic diffraction pattern. This diffraction of the beam of X-ray light is characteristic of light in general. Based on, if you do the diffraction of X-rays by the crystal and measure the angle of scattering, you can actually get information about the crystal itself. Now, here's the idea. If an electron that's moving has wave properties or behaves like a wave, we may well be able to see the electrons diffracted just like X-rays are diffracted by a crystal. Indeed, that turned out to be the case. A stream of electrons passing through a crystal is scattered into smaller, narrower beams at varying angles. You can measure the angle, it's called the angle of diffraction. And that angle of diffraction gives you, in fact, information about the wavelength of the electron. Without going through the details of that, seeing when they took the stream of electrons, they got the diffraction from it. By measuring the angle, they were able to actually calculate the wavelength. The wavelength agreed entirely with the de Broglie theoretical equation. Not too bad. Now, de Broglie insightfully realized that the wave aspect of an electron can explain why an electron in an atom is restricted to having only certain allowed energy values. And Bohr couldn't really answer that. And here's the explanation. When an electron travels in the confined space of an atom, something interesting happens. Its wave is going to wrap around itself. It no longer is a traveling wave, it becomes a standing wave. Now, standing waves, depending on how much you've studied those in a physics class, they're a common observed thing in nature. A guitar string that's plucked will vibrate in a so-called standing wave. If you take a rubber cord and stretch it out and pluck it, the cord will oscillate back and forth. It works like this. If you pluck it with a not really hard, but enough that cause the cord to move up and down, this will do this at a fixed frequency. Let's call it nu naught. This motion is the whole cord moving up or down, up or down. Now, if you actually pluck the rubber stretch cord harder, it will vibrate with a different pattern. It'll vibrate at a frequency which is a whole number, or rather twice the frequency of the original wave. Now, the motion of this higher frequency wave, shown here, it will work like this. The left half of the wave moves up at the same time that the right half moves down, and then it reverses. Then the left half moves down, the right half moves up. So it's an up and down motion, and at the very center there's no motion at all. All the motion in this higher frequency wave is in the portions that are not in the middle. Those portions moving up and down, those are called loops. And that point in the center where there's no motion, that's called a node. Back here in the lower frequency wave, there's no nodes. It's all a basic up and down motion that's called a loop. Or you could also say antinode. Now, if you pluck even harder on the stretch cord, you can get a frequency which is 3 times this nu naught. And here you'll see 2 points in the middle that are nodes, there's no motion, and 3 loops. That's the motion of a stretch cord. It will go up here, at the same time down, and then up. And then it reverses, down, up, down. At all times, there's no motion at these fixed points, the nodes. There's, in this one, three loops and 2 nodes. If you pluck it even harder, you can get a frequency that's 4 times the starting, or the fundamental frequency, nu naught. Here, in this wave, 4 loops and 3 nodes. These are all examples of so-called standing waves. So the assumption is that when an electron is trapped inside an atom, its wave wraps around itself, and the wave is a standing wave. Now, in order to exist, the standing wave must have a whole number of loops. You can't have 1.5 loop for the electron wave. It's got to have a whole number of loops. It could have, let's say, say hole number 1, hole number 2, loops, 3 loops. Each of those possibilities would correspond to a fixed frequency and a fixed energy. That's why the electron is restricted to having specific energy values, because each of its possible standing wave would have a corresponding frequency and specific energy. All right, now moving ahead, this is the 1920s. This is a huge step upward in our understanding of the electron in an atom. There are 2 Germans working actually independently and with different modes of thinking, really came up with a model which entirely is consistent with each other. They both agree. Ernest Schrodinger and Walter Heisenberg. Schrodinger was an expert in wave mathematics, wave mechanics. Heisenberg was an expert in matrix math. Each one was able to describe an electron in a hydrogen atom as basically by its wave properties. And both the theories, both models really agree with each other. Our focus is going to be on the Schrodinger approach. We'll have more to say later on about Heisenberg and his approach and one of the things that he discovered. Well, let's talk about Schrodinger then. He was known to be an expert in wave mathematics. He could, as the story goes, he would be at a dinner party, and if somebody wanted to ask him to write the differential equation for the wave motion of a wave in your bathtub, and you gave him the information, the dimensions, and he would do it. He would write out the wave equation for a bathtub wave. So Schrodinger thought to himself, all right, now if the electron has a wave accompanying it, de Broglie was able to calculate the wavelength of the wave. He said, we should be able to get more information on this wave. We should be able to calculate the actual intensity and amplitude of the wave to get information about the size and shape of that wave. Well, he wrote down, this is a differential equation. It involves second order derivative terms. Gets admittedly a little bit complicated. We'll talk about the details of this equation later. But applying this differential equation to the electron of a hydrogen atom, he was able to solve the differential equation to get expressions for psi and get information about the size and the shape of the wave for an electron at each of its given energy levels. Now, the psi is called the wave function, and the value of it gives the size and the shape of an electron wave. You'll see in this equation itself, E is the total energy of the electron, M is the mass of the electron, V is the possible potential energy. That's an algebraic term that varies with the location of the electron in the space of an atom. But by, as I say, solving this equation for the hydrogen atom, he was able to generate a set of these psi expressions, an algebraic expression that describes the size and the shape of the electron wave in the n equals 1 level, then equals 2 levels, so forth. We no longer say orbits, because the picture that emerges here is very different than really a solar system. We're not looking at specific orbits. The language that we use, instead of orbits, these are called orbitals. Now, let me further explain. The psi expression that you get by solving the Schrodinger equation, as we mentioned, gives you the size and shape of the electron wave. Well, it physically is understood to have even more meaning. The German physicist Max Born, had an insightful thought about the psi function. I'll mention, by the way, that Max Born is the grandfather of Olivia Newton-John, the pop singer. She starred in the movie Grease, if you recall. She now lives in Australia. Well, here's how Bohr's thinking. He suggested that there should be a relationship between the psi value at a given point and the probability of the electron being found at that point. So psi is not only, say, a wave function, but it measures the probability of locating, of finding the electron at a given point in space. We reasoned in this way. It's an analogy of light. Light is a wave. It has a psi kind of expression as well. When the psi value is high, the intensity of the light is high, and if it's high, there should be a high probability of finding a photon at that particular point. So in a light wave, when the intensity is high, the the wave function value for light is high, there should be a high probability of finding the light photon at that point. So the idea is this, is that the larger the value of psi, the greater the probability. Now, he makes a little small alteration there. Psi itself, when you look down, when you get bear down into the mathematics itself, for some higher energy levels, has the mathematical quantity I in it. It's imaginary quantity, so you can't. That means a challenge to the physical meaning that it might have. You can't do a realistic plot if there's the quantity I there, the imaginary quantity, square root of -1. But what is physically meaningful is to take psi squared. When you square a psi expression, it no longer becomes imaginary. It becomes a quantity which has real value. Well, the interpretation is this, that the value of psi square at any point within the space of an atom is a measure of the probability per unit volume of finding the electron at that point. The value of psi square measures the probability per unit volume of locating the electron at that point in space. Now, the word orbit, we, as I say, abandon that idea, but we extend it to the word orbital. The word orbital has evolved from the word orbit. An orbital is not an orbit. An orbital is a region of space within the atom, and it's given by the Schrodinger wave function psi. The size and the shape of the electron's orbital is determined by plotting psi versus position, or equivalent plotting psi square versus the position of the electron in 3D space. Orbital is a defined region of space where the probability of finding an electron is high. Now, we know about orbitals already. We learned that in general chemistry. We learned basically that there are 4 types of orbitals, so-called s orbital, p orbital, d orbital, and f orbital. I'll have more to say about this in class next time. Here is a simple example of sort of the brass tacks of an s orbital. For the electron in this lowest energy state, we refer to that as the s orbital. This is a plot of psi versus the possible positions in 3D coordinate space. It's a little challenge to plot because actually we're talking about an equation with 3 independent variables, and the 4th variable, psi, is a dependent variable. How do you do a plot with 4 dimensions? Well, it's a challenge. In this particular case here, we find that the plot of the s orbital, that when the value of psi is higher, it's shown in the graph as a darker region. And you can see then that the darkest region is close to the nucleus. In fact, when we move further out from the nucleus, the value of psi decreases, it drops, and it's not as dark. It's a fainter in appearance. Well, this is a little crude, this kind of plotting that we're doing, and kind of subjective. There are better ways to, in fact, graphically display the information of psi, and that's what we will talk about in class next time. All right, that's basically it. If you have any questions over what we've talked about in this video, please write them down. We'll talk about them in class, or you can send your questions to email. I'll be happy to respond. Thank you, and goodbye.